right, we're back. Thank you once again for being here to talk about climate and energy at this night at the museum, brought to you by PRI. I am going to cover a apparent paradox of why our planet has a habitable climate when the temperature of the star, the sun, has changed through time. And throughout Earth's history, the amount of solar radiation reaching the Earth, that energy balance that we talked about last time, has changed. And in fact, early on, for most of Earth's history, it probably would not have necessarily been able to have liquid oceans if there hadn't been a different greenhouse effect than the one that we have now. This is called Goldilocks zone and the three planets. We're going to talk about our two nearest neighbors, Earth's nearest neighbors, Venus and Mars. And there's this faint young sun paradox that I just alluded to, which states that if the strength of the greenhouse effect, and remember from last time, the greenhouse effect is required for us to have liquid ocean. And if it had stayed the same strength, same magnitude through time, the Earth would have been frozen over because the sun just wasn't as bright. There just wasn't as much solar energy being emitted billions of years ago as there is now. And the strength of the greenhouse effect wouldn't have been sufficient to overcome that dimmer sun or that faint young sun. And that's the paradox in a nutshell, because the geologic evidence, which you can see all around the museum from these earlier epochs, supports the idea that there was liquid oceans and life in those liquid oceans for billions of years, even when the sun was dimmer than today. And the conclusion to reconcile this paradox is to think that, well, there must have been different greenhouse gases, there must have been a stronger greenhouse effect, and to try to understand what that atmospheric composition must have looked like to have supported life for the billions of years of life's history here on this planet. This curve, these two curves, one is just the intensification of the sun as a percentage of today. The other curve is the expected temperature from energy balance considerations alone, with a greenhouse effect as strong as today's through time. And the dashed line is the threshold for having a frozen planet on the surface, even at the equator, versus having liquid oceans. To get into a little bit more of the nuts and bolts, we're going to reintroduce some concepts of energy, starting with the joule, which I always imagine like a jelly bean. So a joule and a jelly bean. It's not quite one-to-one. A joule is actually less than the amount of sugar in a jelly bean, but it's a good way to visualize just static energy. It isn't doing anything. You haven't chewed it up. You haven't converted it into chemical energy or thermal energy inside your body. It's just there, ready to do work. And it is defined as a Newton meter. So a Newton being a unit of force. So you apply a unit of force over a meter. Well, what's a Newton of force? A Newton of force, hopefully this is familiar, the idea that force is mass times acceleration. So it's going to be mass times meters per second squared, or mass per meters per second per second. So a Newton of force, a single Newton of force, is equivalent to the weight of a small apple. So the weight that your hand, or the force that your hand has to exert against a small apple is about 1 Newton. So you apply that much force over the length of 1 meter, that's a joule. Power is how we measure energy, the scientific unit used for measuring energy. And it's the expenditure of that energy per time. So it's how many jelly beans are you eating per second? That's the energy that you might need. That's the energy expenditure expressed in terms of power. So you take this apple now and you toss it up slowly into the air. And that's not going to require a lot of power, just a few watts maybe at most. But now say you're an Avenger superhero and you can chuck the apple out of the Earth's orbit at 20-some thousand miles per hour at a snap of your fingers. That's going to require a lot of power. And a fun calculation that someone did and wrote up in a scientific journal was to look at how many joules or how many calories the Avengers would need to eat per day to support their avenging. And it turns out it's less than I would have imagined for most of them. It's in the 8,000 to 10,000 calorie range, which is only a little bit more than like Olympic water polo players. So congratulations if any of you are Olympic level athletes. You're using almost as much energy per day as the Avengers do. So watt is how we measure power, and it's joules per second. It's energy expenditure through time, jelly beans per second. We're going to put these concepts around energy into our conceptual model of the climate system, with energy coming in, heating the surface of the Earth in the form of visible light, and long wave radiation leaving. We're going to use the same units for all of this to look at this in more depth. We're going to use watts per meter squared. So this is joules per second per square meter. So the size of the image that's being projected on the screen, it's a little bit bigger than 1 meter by 1 meter. It's almost 1 square meter. And I don't know, but this is probably something like a 1,000-watt light bulb that's inside the projector. So there's something like 1,000 watts, or maybe 500, 400 watts of it, joules per second, 500 joules per second, being deposited on the screen in the form of visible light and then being reflected back out to you. Sunlight's coming to the top of the Earth's atmosphere in the form of visible radiation, shortwave radiation. And just like you can see the projector, because it's reflecting the light, about 30% of the sunlight reaching the Earth is also reflected right back out into space. So right away, there's 102 watts per meter squared that aren't available to the climate system. They never enter the climate system. It's that you were seeing from your distant vantage point when you were imagining seeing the Earth from space. It's that the Voyager spacecraft was able to take a picture of. It's that reflected sunlight. The Earth's albedo is what we use to describe that 30% that's reflected back out into space. So that leaves 238 watts per meter squared available for the climate system to, quote unquote, do work. Work in the climate system is the heating of the surface, the circulation of the atmosphere and the oceans, all the biological processes that ultimately depend on sunlight, which is more than 99.9% of all biological processes are driven by this flow of solar energy. So every single person in this room, unless you woke up this morning and went to the bottom of the ocean floor and fed off of black smokers, you are being fed by the flow of sunlight through the through this energy system, this climate system that's taking sunlight, converting it to thermal energy, or plants are converting it into stored sugars that then are either eaten by plants that are eaten by animals that you eat, or you eat the plants yourself directly if you're a vegetarian. It's the flow of sunlight that's keeping us all alive. Not only keeping the planet habitable, but literally keeping us alive right now. That 238 is an average. It's an average over space, and it's an average over time. So some of you might know, if you have solar panels on your roof, that in the peak of the day in summer and even through fall and spring, there might be 1,000 or even 1,200 watts per meter squared at the peak of the day. But this is an average throughout the entire day, throughout the entire year, that gives us this 238 watts per meter squared to work with. And a climate system that were in balance would also have to emit 238 watts per meter squared on average back out into space. Otherwise, it would be warming up or cooling down. If it was out of balance, it would be either losing more energy than it was receiving, or it would be trapping more energy than it was receiving, in which case it would be heating, or it would be cooling if it was losing more energy. And to look at this a little more quantitatively, we're going to introduce a very simple relationship that just happens to have a fourth power here. So this is going to be the Stefan-Boltzmann law, which relates the total amount of radiant energy to some constant. We'll call this sigma. What the sigma? Well, it is 5.67 times 10 to the negative 8th watts per square meter per times Kelvin to the 4th. The units aren't going to be super important for what we're going to do in a second here. Times temperature to the 4th. So some constant, sigma, times temperature to the 4th is going to give us a radiant energy. Since this is a constant, it's just a number. It's the same everywhere in our universe. We don't need to think about it changing. What we think about changing is the temperature. And this is where as temperature increases more and more, the amount of radiant energy that's emitted by an object also is going to increase. And it's going to increase exponentially. It's going to increase as a fourth power of the temperature. We're going to use that to solve for an equilibrium temperature. Rearrange the terms, divide by sigma, take the fourth root of the emissions in radiant energy emissions. So that 230 watts per square meter, take the fourth root of it after we divide it by sigma, and this gives us an equilibrium temperature. This is the temperature the surface of the Earth would have if there were no greenhouse effect. Can you think of an object near us where this temperature equilibrium might be applicable? That doesn't, a smaller than our planet, bigger than an asteroid. The moon, did you say? That's correct. The moon. Right, so the moon, the equilibrium temperature for the moon, which doesn't have a strong greenhouse effect, doesn't have greenhouse gases because it doesn't have an atmosphere. It's like, you know, what they say about the restaurant at the moon, right? Great food. The food's out of this world, but no atmosphere. Stand up for climate change. The equilibrium temperature of the moon or the equilibrium temperature of Earth with no atmosphere would be something like 255 K or negative 18 Celsius or just below 0 Fahrenheit. That's why you and your extraterrestrial colleagues would have concluded that this planet should be frozen over. We shouldn't have liquid oceans unless there were a greenhouse effect. This gives us an intuition for the greenhouse effect here on Earth. We're gonna do this with all of these three neighbors, so Venus, Earth, and Mars. We're gonna do the same exact calculation again to look at the equilibrium temperature for each of them. So for Earth, the equilibrium temperature is 255. For Venus, the equilibrium temperature is colder. It's 220 Kelvin. What is going on there? It's not an intuitive result. Any hypotheses for what could be happening? The equilibrium temperature for Venus is colder than Earth, but we know it's a lot hotter. Russians sent a space probe there and it melted within like 45 minutes, like the 70s. It's this term, the albedo. It's very reflective. So its energy balance, it actually has less energy, total energy to work with in its climate system than Earth because it reflects so much from those shiny, bright clouds. And that's why you see Venus in the morning or in the evening. It's so reflective. It's so bright because it's got all these clouds made from poisonous gases, as it turns out, reflecting light back out into space. So its equilibrium temperature is 220 Kelvin. Mars has an equilibrium temperature of 213 Kelvin, not that dissimilar from Venus, both of which are colder than Earth's equilibrium temperature. Now we look at the actual surface temperatures. So the actual surface temperatures on Venus are almost 500 K warmer, 730 Kelvin, the actual surface temperature on average. That's because it has a monstrous greenhouse effect. Its atmosphere is like 95% carbon. And so all that heat just gets trapped near the surface. The long wave radiation gets absorbed and re-emitted and absorbed and re-emitted and absorbed and re-emitted many, many times over before it can escape back out to space and it gets trapped close to the surface. Mars has a very thin and weak atmosphere. It's weak greenhouse effect in its atmosphere. So its equilibrium temperature is close to its actual surface temperature. So it's a very weak greenhouse effect of only about 5 degrees Kelvin. And then Earth's greenhouse effect is equivalent to around 30 some degrees Kelvin, or 30 some degrees Celsius, 30 some Kelvin. The corrections folks will definitely troll me if I say degrees Kelvin. I know this. I know not to say degrees Kelvin. I see you all over there. Degrees Celsius or just Kelvin. Now on Venus, it's a little bit of another paradox. Why doesn't it have a more habitable climate if it's so reflective and has less energy to work with because of the greenhouse effect? Well, why did all that carbon in Venus's atmosphere end up in its atmosphere and not trapped in the rocks like what happened on Earth? And the short story, the short version of the story, and Carl Sagan, again, was one of the first to work this out and hypothesize about how this may have played out. As this sun got brighter and brighter, you would have maybe had a situation where there once were liquid oceans on the surface of Venus. And that carbon-rich atmosphere would have made life, at least life as we know it, possible on the surface of Venus with that colder, dimmer sun. The warmer, colder, dimmer sun. As it warmed up, though, the water vapor in the atmosphere of Venus, which is also a potent greenhouse gas, would have accelerated the warming. And as you accelerated the warming from temperatures getting warmer, from sun getting brighter, now you have water vapor acting like a greenhouse gas and accelerating the warming even more. But that's not where it ends, because we have on Earth most of our carbon trapped in the rocks. And to get carbon trapped in the rocks, you need chemical reactions that involve liquid water. And so in the early stages of Venus's history, that liquid water became less and less abundant, potentially, as the star started to warm up. The CO2 wasn't removed from the atmosphere quickly enough to escape its fiery fate as temperatures got hotter and hotter on the sun. Energy from the sun continued to warm the planet. More greenhouse gases from the water vapor led to more warming. Less CO2 was getting trapped in the rocks. It's a runaway positive feedback that resulted in eventually there being no liquid oceans and a monstrous greenhouse effect on Venus over billions of years of timescales. Billion-year timescales. We'll fix it in post-production. It'll be fine. Now, Mars represents an even more extreme version of the faint young sun paradox, because now we have very compelling evidence, very strong evidence that there were liquid oceans on Mars once upon a time. And yet it's farther out from the sun than we are. And that requires it to have had a much thicker, much more potent greenhouse effect early in its planetary evolution. And to understand what probably happened on Mars, we need to think about the structure of Earth first and how it has a solid iron core surrounded by a liquid layer that allows that solid iron core to spin and create a magnetic field. And that magnetic field, the whole Earth acting like a giant magnet, deflects solar wind and protects the Earth's atmosphere from solar wind. Mars being smaller and cooling quicker meant that that process, if it happened at all, would have stopped sooner. It lost its magnetic shield, it lost its protection from solar wind, and over billions of years, its atmosphere eroded away, leaving it with this very thin, weak greenhouse effect. And as far as we know so far, no evidence of life, certainly not life as we know it. So early Mars suffered the fate of its small size, and it's too cold, but not necessarily for the reasons that you might think intuitively. It's not just because it's farther out. In fact, it may have been in the habitable zone with a much thicker atmosphere, even though it's farther away from the sun, just because of its early greenhouse effect. And we know that it must have had liquid oceans, which requires it to have had a stronger greenhouse effect than it does now, because now its surface temperatures are too cold. And so that's how we get to Earth being just right. And it's been just right for life, multicellular life for a little over 500 million years, unicellular life for several billions of years, as you'll see as you walk around the museum. It left it just right, but it's the role of life that in part has governed or has made it possible for the climate to remain stable. And so in the reading that's been assigned to the class, Pierre Humbert says we shouldn't be calling this the faint young sun paradox. We should be calling this the habitability problem. How do you get a planet as unique as ours, a unique planet, 4.5 billion years on this unique planet, that has had a stable enough climate system, even when the sun's output has changed by 30%, which should have corresponded to much more climate change than has actually occurred on Earth. And it's the role of life in part, and the global biogeochemical cycles associated with life, that have helped stabilize the climate through time, that help resolve not only the faint young sun paradox, but also what Pierre Humbert calls the habitability problem. We'll leave it there, and then we're going to talk about when things go awry, when life starts to affect its atmosphere in ways that have positive feedbacks that lead to cooling.